Like X-ray, you saw the images, they would be basically gray-scale images. Analysis of those images would be basically done by extracting the features as we talked about. So for example, you could extract the features, histogram features, you can extract the moments, you can extract the gray level based features or the GLCM or GLRM features, and those features then you would use for classification. So basically what changes in the different types of imaging systems is how you are acquiring the image. Once you acquire the image, the analysis part remains the same, whether the image is coming from visual spectrum or X-ray, or from now we will look at the thermal imaging system. Okay. So this particular picture shows the thermal imaging system, and in this again I hope you can see now the light intensity have changed. So what you have, this one here is the thermal camera. Number one is the thermal camera, and that basically is going to give you the image. But in this particular one, the number 2 is the close-up lens. So that is basically shown here, and that would basically move closer to the sample or allow you to move, maintain the constant spatial distribution. Then 3 is basically your PID controllers to control the, and I would explain why that PID controller is needed in this particular example. PID controller is nothing to do with the thermal camera to take the images, but it is to heat the sample, and I would explain that. And then number 4 is basically again you acquire the image and then do the data analysis. So in the thermal imaging system, what you are looking at is the like any object, and does not matter what the material is. Every material you would remember from Stephen Boltzmann law, if the temperature of a material is more than minus 273.15 degrees centigrade, it would emit heat. And you are basically trying to capture that heat being emitted from that object. Okay? So every object does that, and what you are trying to capture is then the temperature distribution of the material. So thermal camera basically gives you the temperature distribution or thermograph, and then basically once you have captured that, then you basically get the image and then you do the analysis. Now so what we hypothesized was that and again I would take the example of the sound grain and insect infested grain. So if you have the sound grain and you have insect infested grain, if you heated that for say 10 seconds, the sound grain would heat differently than the infested grain. Okay, which means then, so if you had the grain, both the infested grain and sound grain at the room temperature, you heat it for 10 seconds or 15 seconds by a particular mechanism, and then as soon as you finish the heating, you take the picture using the thermal camera, which is measuring the temperature of those objects. So you would be able to see the difference of the temperature difference would be, you would be able to detect then which kernel is infested or which kernel is not infested. So in the what you see in the below the lens, white color platform, that is the constant temperature plate, and that's why the PID controller is needed to create that constant temperature of that plate. So what you would do is you would put the sample under the camera's lens or in the camera's field of view. You would bring this heater over the top of the sample there for 15 seconds, move it away, take the image, and then do the analysis, and you'll be able to do the detection. So that's why the PID controller is needed. It has nothing to do with the camera. It is more for that heating system for this particular application. You could do the cooling or heating, because what you are trying to do is that you are trying to capture is the differential rate of heating or cooling, and that's where the difference is coming in the thermal imaging. Okay. So the origin of the thermal imaging dates back to 1800. This is when the William Herschel was working on looking at the sunlight, or looking at the sun rays, and he was using the prism to basically look at those 7 colors you see in the rainbow. And not that he was trying to discover these rays, he put the thermometer outside of the red spectrum, or outside of the, so the sunlight was coming through the prism, and then it is split. So 7 colors you can see, but he basically by chance put the thermal camera beside the red color, and the temperature started rising. So he was the one who found that beyond the visible spectrum, or just beside the red, there was a heat being generated from the rays, and that he called them calorific rays, which basically means that they have energy in them. So that's what the first time the thermal imaging really started, or not thermal imaging itself started, but the concept of the infrared rays having the energy or heat value was conceptualized. And then for almost 80 years nobody worked on them. He made that discovery, but nobody worked on that. And then so in 1880 was after 80 years, Langley is the one who invented the bolometer, which was used to measure the infrared to heat radiation. So be able to measure that, quantify, like basically Herschel did was he just said that these are the rays which are high energy rays, but he didn't know what to do with them. It's the Langley who then was able to determine what the quantity of that is. And then another 30 years or so passed, or 40 years passed, or I think almost like 50 years passed, 1929, when the Hungarian scientist Tihany invented the infrared sensitive electronic television camera for anti-aircraft defense system. So the real time when the first use of the thermal imaging was used was in 1929. So for example, in the anti-aircraft defense system, what it was detecting was any activity happening. If you are flying the aircraft and you start scanning the surface, if there was a factory, naturally there would be much higher heat activity in that area, and you'll be able to detect that. Now these thermal cameras are used in many applications. Like, so for example, if police was looking for a fugitive who has ran into the deep forest, by scanning the canopy of the forest, wherever the person is, his body temperature or her body temperature would be higher, they be able to detect where that person is. So basically you are looking at measuring is the temperature difference, and that's what you are then exploiting for your application. Okay. So then in 50s and 60s, a single element detector to scan the scenes and produce the line images was developed by Texas Instrument, the same one which builds the calculators, or were popular calculators, along with the Hughes Aircraft and Honeywell. And that's where basically you would say the modern thermal imaging started, was after inventions by the Texas Instrument. And thermal imaging technology initially was developed for the military applications, as I said, but now they are used in firefighting. So to detect the hot areas, when the firefighters would go in the fire-prone area, they can use the thermal camera to see where the heat is coming from. So they can identify the source of the fire, for example. Law enforcement, I already mentioned, to detect the fugitives or find the people hidden in the areas. Security, the same thing. If you had a thermal camera installed and somebody walks through, heat would basically can trigger the alarm. You don't have to use the thermal cameras. Even the normal cameras can do that, the same thing. If somebody walks and then you see the light intensity broken, for example. In the transportation they are used, in industry and agriculture, food. food and agriculture, and many, many other industries. So thermal cameras measures the infrared energy emitted from the surface of the object, and that temperature distribution on the surface of the object is converted by the thermal camera into a pattern or a map, and that's what is referred to as a thermogram. And then thermogram really then becomes your image, keeping in mind the intensity now is not the reflectance, or with the X-rays, not the attenuation of the X-rays, but rather it is temperature. So every point or every pixel would give you the temperature value. Now the temperature value could be similar to the gray level. The temperature values again could be 1.2, 3, 5, 25, 100, 1200, depending on what the temperature what kind of temperature field you are working in. But so every pixel now has the known temperature value rather than having the known gray level or known R value or G value or B value. So that's basically what the difference would be. So image then in the sense is the analysis can be done the same. You replace the gray value by the temperature value. Okay. Thermal imaging systems operate in two wavelength ranges, 3 to 5 micrometers. And they are referred to as a mid-wave infrared thermal imaging system, or 7 to 14 or 8 to 14 micrometer. They are referred to as a long-wave infrared. And these are the basically two ranges where you can buy the cameras for thermal imaging. The region thermal imaging has become a very powerful tool for detection. Is the current version of cameras, thermal cameras, sensitivity or the resolution of those cameras is 0.03 degrees centigrade or 30 millikelvin. So 0.03 is a very small change in the temperature. So if you were the example I was giving, when you are heating the infested and uninfested kernels, you only need to have a slight difference. So even if it was a half a degree centigrade difference, you could then detect that, because of the camera sensitivity being such a low 0.03. Theoretically, even if you had a 0.1 degree temperature difference between the two objects, you would be able to detect that because of the such a high sensitivity. Another area, and that's why I think when the SARS or H1N1 I think hit the population, they were able to install these thermal cameras in the airports or wherever you need to measure, and without even person knowing, they be able to detect the higher temperatures, because human body temperature is a constant temperature, and if somebody had a 1 degree centigrade higher temperature, you would know that they have the symptoms, and you can, because of sensitivity of the camera, you could detect that 1 degree centigrade difference. Okay. So I already mentioned that all bodies or all materials emit energy as long as they are above 0 Kelvin, which is a minus 273.15 degrees centigrade. Infrared radiation then has the wavelength from 0.7 to 1000 micrometers. It could be classified near, mid or far, depending on whether you are close to the red, then it would be near. If you are farthest part of the eye, closer to the like furthest away from R, it will be far, and in the middle range would be middle. So basically that's what it's referring to, the near, mid and far infrared radiation. An amount of radiation emitted by any object depends on naturally the temperature of the object. It also depends on its surface conditions or surface characteristics, and the thermal properties of the object. So like particularly the emissivity of the object basically would dictate how much heat is emitted, and that's what you're detecting. A black body, which is also can be seen as an ideal absorber, absorbs all of the radiant energy. At the same time, it emits the 100% of energy, and that's why it is called an ideal body, but really does not exist in the reality. So because all materials would have emissivity or absorptivity coefficients and transmittivity coefficients, which are the ratios of the radiation being emitted by the body to the black body. So that's basically, but the black body really is the concept, but is the absorbs all radiation or emits all radiation. Now, in terms of the applications of thermal imaging, it has been used for many applications, and there are many more. This list doesn't include all of the possible examples. So soil water stress, soil water status. So for example, to find out the soil moisture, you would have to take the physical samples, then do the evaluation using bring it to the lab. You would measure the moisture content typically with the oven drying method. Whereas the thermal imaging is again, because if you have a different moisture in different parts of the soil, then you would have different radiation or different emission coming from that part of the soil. So by taking the thermal camera and taking the image of the soil, you'll be able to detect which parts of the soil have less moisture and which part have the higher moisture, as an example. Measurement of the leaf temperature, particularly if you're looking at the transpiration properties, and then you are looking at even the distribution, whether the moisture is being lost from which part of the leaf, that kind of distribution you'll be able to look with the thermal camera. Irrigation management is another example where thermal cameras are now quite frequently used, where you would have the crop canopy, and the crop canopy temperature would basically tell you whether the plants are under stress or not. And then knowing that plants are under stress, you can turn on the irrigation system. So most of the irrigation, automated irrigation systems nowadays would use a thermal camera to turn on the water irrigation, automated irrigation system. Could be used for detection of the insect and fungal damage in grain, and that's where our lab has done a lot of work using thermal cameras for insect detection. Actually, Chela did some work in this area. Quality of fruits and vegetables, again the same thing. So like if you had the apple, for example, and the surface of the apple was damaged by mechanical damage, the tissue would basically, and if you again exposed to a slight amount of heat, the damaged tissue would heat differently than the sound tissue would heat, and you'll be able to detect where the damage is, for example. Even though the skin on the outside might look perfectly okay, but the internal damage, it be able to detect that because of that difference in the heating. Harvesting and yield estimation, again by looking at the temperature distribution on the crop canopy, you can make the predictions of the yield from the field. Detection of foreign bodies in the food, again the same concept is like the way I explained the infested kernels. Like again, if there is a foreign body in the material, and if you expose to a differential heating, and whether that's a meat piece or any other material, would heat differently than if it was not present. So you are basically trying to appreciate that. Meat would be the similar applications, and in the meat in particular, you could also look at the changes in like on the first day I was talking about the stressed animals, and the meat properties are different than the unstressed animals meat. So when you do the slaughtering, and again they would react differently to the heating system. The surface temperature of the food, certainly you can easily measure. An estimation of the body temperature of the pigs, as I was explaining for humans, you can do for pigs, for cows, so many applications. The one thing to keep in mind is that it is a surface temperature measurement phenomena. It does not measure the temperature inside the body. So to give you an example, like for example, in the large, let's say, grain bin, and you have the grain is spoiling in the middle of the bin, it would not be able to detect that grain spoilage in the middle of the bin, because the amount of time it would take for the heat to move from that spoilage area to the surface would be quite long, because grain is very good insulator. So you would not be able to detect that, because but on the other hand, that spoilage, if it was occurring closer to the wall, then the wall would see a temperature difference and you'll be able to detect that. So that, the one thing you have to keep in mind is that it is measures is the temperature differences on the surface of the object, but not inside the object. Okay, and anytime you can detect that, it's thermal imaging can be used. So in the example I was giving, so here on this picture you can see the plate, which is a grayish color in there here, whereas the image I showed you was white plate. It is the same plate, just got painted. So in this case, it's away from the sample, whereas and then you would bring it on top of the sample, which is the wheat sample sitting in the field of view of the camera, and then you would take basically the image. And as you can see in this case, and the two images you see there, the grain with the insect inside, so you can see the difference coming about there. Okay. And whereas the and then depending on where the larva is, you'll be able to detect that, and sound grain would not have that kind of intensity difference. A few other applications of the thermal imaging in the food industry, like for example, to maintain the quality of the potatoes during storage by monitoring aeration and temperature changes. So if when you do the aeration control, you are trying to maintain is the constant temperature, and if you don't maintain the constant temperature, then the browning reactions can happen in the potatoes during French fry making or frying. And for the table potatoes, for the household, it would not have any effect, because you are typically making mixing with the curry or spices, so it would not make much difference. But particularly for making French fries or processing potatoes, it becomes very important, and you need to make sure that the temperature is not varying too much during storage. Detection of foreign substance in the food materials, or inspection of the cooking process for the chicken, identifying overcooked or undercooked chicken. And the example given there is when you are doing the processing of the chicken fingers, the temperature measurement is being checked to look at the undercooked chicken fingers, for example. Okay, and it will be able to detect those undercooked. And the image on the right hand side is the thermal camera image, and then one on the left hand side is the what you would take with a normal camera, or how the processing line will look. Other examples in the food area would be the temperature measurement of the bakery products to maintain the quality, or you can so that you have uniformly heated the bakery products, or temperature monitoring during the pelleting process of the feed manufacturing. When you are making the pellets, you want to have the uniform temperature, otherwise your pellet would start disintegrating. And the examples given there are examples of the thermal image for the chocolate chip cookies, and then you are trying to identify you can identify even the areas where the chocolate chip is missing, or you can identify the uniformity of the heating using the thermal cameras. Okay, so any questions on thermal camera? Very simple concept, and we are measuring basically the temperature differences. Yeah, go ahead.
Does it lead to wrong interpretation of results? Like same heat, it is measuring the thermograph right now, measuring the heating behavior of an object. So if we are estimating the grades like rice, and if suppose the barley is also coming along with and emitting the same heat, so does it differentiate between the two or not?
Okay, so now again, so the example you are saying, so like for example, you had a rice kernel and you had a barley kernel or wheat kernel, and if the respiration rate of the kernels is different, then you would be able to use thermal imaging to identify which kernel is which, for example. If the respiration rate is the same, then you would not be able to. Okay. So what you have to understand is that the material you're dealing with, how you would create that temperature difference. Like it could be the natural temperature difference. If the one kernel respires differently than other, then naturally they are differential heating. you'll be able to detect that. The example I was giving in the infested and uninfested kernel is when you have a sound kernel, and if there is an insect inside because of that hollow cavity, and if you bring that plate on top of that for a few seconds and then remove that plate, the sound kernel would heat differently than the so naturally the infested kernel would become more warmer because it's much hollower, less material to heat. And we are talking about detecting only half a degree